Okay. I've talked about current density. Um, I didn't really. It's implicit the drift velocity is proportional to the field and the current's amount of charge drifting past a point per unit of time. It means that I didn't leave myself room to write it. Okay. I left this out. I do apologize. For given material, your current density depends only on your electric field. Okay. Okay, you're in nichrome. Doesn't matter where you are, in some little minuscule part of this wire or in a big old chunk of nichrome. Okay. If I want to get my current density, that's the amount of current per unit area. I just figure out my electric field at that point and multiply by that constant. So the current density is the same at every point where the electric field is uniform. Okay. Now, when we come back to this situation, two nichrome wires, two different diameters, same length, same voltage. Okay, same length and same voltage means we have the same electric field. Okay, meaning that the current density is going to be just some multiple of that electric field. It doesn't matter which wire we're in. Okay, so they both have the same current density. So both wires have the same current density. So what's the ratio of the currents? Okay. Okay, so we're going to have current density. But writing very well today on the current density change. Thus, ratio of your currents is going to be J, whatever it is, times the ratio of your areas. Okay, well, what's the ratio of the areas? I didn't give you the areas, I gave the diameters. Okay, so, what I've been getting, and trying to get us out of here is the idea that the ratio of the areas is D2 over D1. It's not the ratio of diameters. We're talking about area. So squared ratio of the diameters, okay? And the problem is, I think the image people were carrying, because I know one of you, at least in some of your reasoning, was thinking about the surface. Okay, like the surface of the outside of the piece of water, okay? Like the outside surface of the pipe. Fluid doesn't flow through the boundaries of the pipe, it flows through the interior, okay? And the electrons are not distributed on the surface, although if you know electrostatics, you know that for okay, net charge is going to be on the surface of the conductor, and I think maybe that's where the confusion is coming from, okay? This is not a net charge. The net charge on this whole nichrome wire is presumably zero. It's presumably neutral, okay? It's not holding any static charge on the surface. It could be, but probably not, because it's probably grounded. Um, so you want to get away from the image of the charge being distributed over the surface. Okay, charges throughout the material and the flow of charges throughout the interior of the material. Okay, took me a while to catch on to the idea that that was why you kept wanting to just do the ratio of diameters. And that would have been correct if it was just flowing along the surface of the material. And there are topological materials where you do have flow just over the surface. But we're not getting into that at all. Okay. Okay, well, there we have it. Okay. So we'd have this. Now, what if we do the same thing? Let's draw it a little more explicitly. Now, the symbol for resistor is this. It's like, okay, these two resistances might be two different pieces of nichrome of different diameters and different lengths. Okay, so let's say these are both nichrome. So these are both nichrome. They both have a length. Each has a length and each has an area. Okay, so what's the ratio? Of the currents? You have some source voltage or some voltage across here, whatever that voltage is. Might be. How do you get the ratio of currents? Okay, we have this conjecture from somebody who's usually right. We'll see if that, and everybody seems to agree. Okay, so let's see if it works out. Okay, if we want to get the ratio of the currents, we want to go back to current density. You'd have different current densities since you got different lengths, right? So J1 some constant times Z1, J2 some constant times Z2, right? And it's the same constant. So that J2 over J1 is certainly equal to E2 over E1. Now let's digest that, make sure we understand that, because we really want to develop the feel for this current density thing. Because it's kind of the idea that we pivot everything on. Okay, so now E2 over E1, well, I mean, we can say, the electric field is just a number of volts divided by a number of meters. It's your electric field divided, or your voltage divided by your length. So that would be V over L2 divided by V over L1, which is L1 over L2. So that the lesser length will have the greater field. Okay, or the greater current density, well, the greater field, because your voltage is spread out over less distance. Again, the introductory problem sets, the language of the introductory problem sets, the reasoning of the introductory problem sets is very clear, I think, and very simple if you simply get used to it. And you can easily use that as a basis for cutting through a lot of complication, which is the whole purpose of the thing. Okay, so we can erase this. There's some correction made, and I think it sounded right, but I didn't want to listen that hard. So we'll work it out in detail. Okay, so there's your J2 over J1. We want the ratio of the currents. So we've got the ratio of the current densities. How do we get the ratio of the currents? Well, how is current density related to current? Your current ratio is each current is a ratio of its current density times the area. So we have this. And of course, J2 over J1 is L1 over L2. Now, if you just think this through in terms of what's directly and what's inversely proportional, you can say, well, okay, your current density is going to be inversely proportional to the length and directly proportional to the area. There's inverse proportion to the length, direct proportion to the area. We talked a little bit earlier about the deficiencies people have not having had physics in high school and so forth, and the fact that, there's things you gotta think a little bit harder about. And by the time you get done at Tech, you should be do well over any of those deficiencies, but another deficiency people tend to have. And I think it's nationwide, but it might be a little worse here than other places. The whole idea of proportional thinking. I mean, this is an inverse proportion to the length and directly proportional to the area. And being able to think about what's inversely proportional, what's directly proportional in a more complex set of parameters gives you a much deeper understanding of a system. And it's much more efficient than having to work through all the details of the arithmetic, okay? So all I'm saying is you really need to understand proportionality and variation. And I think I said that before, look it up. Spend an afternoon on proportionality and variation and start to incorporate it into your thinking. When you get a chance, and I know, of course, the way stuff comes at you, it's hard to do that, but it'd be well worth your trouble, I think. Okay, so there it is. Okay, well, that's a fairly good start on a model of current flow. Okay, and an understanding of resistors. So we can say, hopefully it makes some sense now, okay, to make a definition of for given potential difference, for given voltage, current flow is inversely proportional to length, directly proportional to cross-sectional area. Now there are more qualifiers. I'm assuming some material, some uniform material, okay? So careful about my terminology. Well, I think I want to say conductors. Could be defined as constant times cross-sectional area divided by length. A lesser length, it's going to tend to conduct more for given voltage. A greater cross-sectional area is going to tend to conduct more. Okay. Now there's a symbol for this, and I should have looked at the symbol. And I'm sorry, I've been trying to recover from last week's illness. And it really did kind of knock me for a loop. So I didn't get to look at everything I wanted to look at this morning. Let me take a quick peek at something here. Just symbols. Well, there's a symbol for conductance. I haven't used it in the last year and I don't remember. I'm still a little bit brain fog. What the symbol is. So I'll just cut to the chase. Resistance it's a reciprocal of conductance. Okay. Oh man, chalk. Or places chalk us to kind of skip there. I really don't like to look at a bad row. Okay. Rho is going to be the reciprocal of this constant here. It just depends on the material. So rho is just a constant that determines, this is determined by the material. Property of the material. We run known voltages through different samples of the material, different diameters, different lengths, and so forth, measure currents, and we come to conclusions about resistivity, and we can measure that very precisely for given materials. I think Rho's values of Rho are typically in the order of 10 to the negative eighth ohm meters, but I haven't told you what ohms are. Okay. If I multiply conductance by voltage, I get current. Therefore, if I multiply voltage by the reciprocal of resistance, I get current. Okay, I'm just going to wave my hands over this. This is what we multiply by the voltage to get current. Just go back to everything we talked about and try to understand that. This is the reciprocal of this, or this constant here is the reciprocal of rho. And rho is what we usually work in terms of. So here's what it comes out to. Voltage times reciprocal resistance equals to current. This goes back to this. There's your connection. So we now have V equals IR. Ohm's law, we usually throw that in capitalized Ohm's name. Okay. If you want to get the resistance of a circuit element, you put a voltage across it and measure the current. Divide the voltage by the current. The unit of current is the ampere. V is in volts. So resistance is in volts per amp. Or ohms. So that's basically what an ohm is. It's just a name for the constant that relates current and voltage. Okay. There we have it. Okay, well, that's great. But we want to talk about energy. Okay, what about energy in a circuit? Okay, well, there's conduction. So now let's say that we have some resistance, and we have a current I through this resistance. Then your voltage will be the product of your current and resistance. What do you get when you multiply current by potential difference? Well, it'd be amperes times volts. And yeah, and so we had a good observation. Yeah, current times potential difference would be I times IR, which would be I squared R, which is also V squared over R. But we're not there yet. We're trying to get what I'm trying to get to is the meaning of current times potential difference. So, and we're getting to power. You know, what we just said was the definition of power. Okay. So we got amps times volts though. What's an amp? It's a coulomb per second times a joule per coulomb. Now, coulombs are no longer fundamental units, but we still can understand what an amp is as a coulomb charge per second. So if we multiply coulombs per second by joules per coulomb, what do we get? We get joules per second which is our unit of power. Okay. Power equals current times voltage. And that's your basic power relationship for circuits. And of course, that's I squared R or V squared over R. Just alternative ways of doing it. V is the current times resistance because of all the connections we made here. And this connects to this very easily. The current's V over R, so I squared is V squared over R squared, so that IR is V squared over R, and everything comes out very nicely. And those are easy relationships to understand and manipulate. Okay. So that's what it comes down to. So if you do as I recommend and look at your introductory problem sets soon after class, you'll see that there's a lot of reasoning around energy and power and models of conduction. Okay. And be well to spend a little time on that before next time so we can put it together. And you'll understand it better if you spend a little time on it. Okay. So I know what it's like between Monday and Wednesday, so I don't expect miracles, but do the best. Okay.